Hi, welcome to the video about code quality metrics. My name is Valentina Pakhomova and I'm a front-end developer at Wrike. I work in an internal team, and this means that apart from doing traditional front-end stuff, I also get to work on some cool technical tools that help to improve processes in our front-end department. And actually, out of working on one of such tools, the idea for this video was born. But keep in mind that everything I'm going to talk about is applicable not to just front-end, but to all areas of development where you get to write the code. And before we start talking about code quality, I have a small question for you. Are you sure that the code that you write is good? And why do you think so? Answer in the comment section below. We'd love to hear from you. But what is good code anyway? Obviously, it's the code that works. And it does what you told it to do. And more than that, it should do so efficiently. Additionally, good code should not produce bugs. And good code should be maintainable, meaning that it should be easy to read the code, easy to make changes to it, and easy to understand it. And if everything is easy enough with the first item, I hope you check your code at least once before you push it to master. With the last two items, it will be obvious only after a period of time if your code matches them or not. And we can even say that the last two items are interconnected. Let's say that you have a huge function that has more than 500 lines of code. It will be hard for you to write proper unit tests for it. It will be easy not to notice some logic mistakes during code review. And if you were to make changes to it, you risk potentially breaking some logic because there's a lot of it in this function. Apart from potentially causing bugs, unmaintainable code makes other people suffer. Imagine if the developer had to go and make changes to your function. They would open it, they would think, oh my god, and they would spend a lot of time and resources trying to understand what's going on there. And I'm even sure that at some point they'll open git blame, look at your name, and say, screw them. So I strongly believe that we should pay attention and make sure that our code is maintainable from the very beginning. Because once you get your code into the master, it stays there for a long time. Not many people will allow you to rewrite code purely for the sake of rewriting because you always have pressing deadlines and new tasks to complete. So how can we ensure that the code is maintainable, and how can we do this from the very beginning? We can't just tell people, can you please write good code and not write bad code? Because, well, even the best of us have bad days where we tend to turn blind eye to code standards, and we push not our best code to the master. And this happens because we have deadlines, and we just want to go home early. So we need to ensure maintainability, and we need to do this automatically. But how can we do that? And the answer to this question is using code quality metrics. So code quality metrics are basically measurable aspects of your code and reference values that tell you whether your code matches a certain standard or not. And the list of those metrics is actually different from company to company, and everyone puts in this list what they find to be the most important. So today we'll talk about code quality metrics and reference values that are commonly used by the community and the ones that our company found to be most important. Additionally, I'll share the ways of how can you use those metrics, and we'll talk about how we do this at Wrike. Let's start with some simple metrics. The first one is lines of code. If your function has a lot of lines, it indicates high complexity of the function, and it will be hard for you to read it and to make changes to it. So the community agrees that if you have less than 50 lines of code, then it's very good. If you have more than 100, then it's bad and you should consider refactoring your function, for example, splitting it into smaller functions. The next metric is number of arguments. And if you have less than 4 arguments, then it's very good. If you have less than 8, then you should also consider refactoring. Because if you have a lot of arguments, it will be hard to make new calls of the function. And if there are already a lot of existing calls, it will be hard to make changes to all of them. For example, if you had to add another argument and the function is being called from 7 places, you'd have to go to all these places and add this new argument. The next metric is number of methods, and this is a metric for a class. If your class has too many methods, it indicates high complexity and shows that probably your class is doing something that it shouldn't do. And it could be refactored by splitting the class and moving some of this logic to another smaller classes. So if you have less than 10 methods per class, then it's very good. If you have more than 20, then it's not okay. And it's starting to get hard to understand and read the class. The next metric is maximum nesting. And nesting is when you put one code struct inside of another. For example, if you put one if block inside of another and so on. So if you have less than 5 levels of nesting, then it's good. If you have more than 10, then once again, refactor, because it's starting to get really hard to read. Next metric is called Cyclomatic Complexity, and it's a metric that shows the number of linearly independent paths through your source code, or simply speaking, the amount of decision logic in your code. And if we present our code as a control flow graph, which is a graph that shows all the paths that can be taken while your program is being executed, we can calculate cyclomatic complexity as the number of edges minus the number of nodes plus 2. Let's look at an example. So we have this small piece of code here, and it can be represented as a control flow graph that looks like this. So the number of edges here is equal to 7, which is basically the number of arrows in this graph. And the number of nodes is also equal to 7. So we get a cyclomatic complexity equal to 2. And the reference values for this metric is if you have less than 20, then it's very good. If you have more than 20, then it means that there's too much decision logic, and once again, it becomes hard to maintain this function. And the last metric I will cover in detail today is called Maintainability Index, and it's a complex metric that shows you the relative ease of maintaining your code, and it's proportional to Halstead Volume, Cyclomatic Complexity, and lines of code. And Halstead Volume is the metric that shows the size of your program based on the number of operators and operands. But this metric, this function, looks a bit too complicated, so let's try to calculate it with me. So as I've said, Halstead Volume depends on the number of operators, operands, and as well as the number of distinct operators and operands. So if we look at the code example that I showed you earlier, this piece of code has 9 operators, 6 of which are distinct, and it has 15 operands, 6 of which are distinct. So if we start putting the numbers into the function, we will get the Halstead Volume equal to 86.3. And now let's return to the Maintainability Index function. So we've calculated Halstead Volume right now, and we've calculated cyclomatic complexity earlier, and the number of lines of code is equal to 6. So we get a number equal to 118.35. But with this formula, we basically can get a value from 171 to any unlimited negative number. So we need to put the value that we get from this formula into the range from 0 to 100. And we can do this by applying this function. So finally, we get the maintainability index for the piece of code that I showed you earlier, and it's equals to 69.2. And actually, this metric is sort of Australian because the values here are reversed. If you have a small amount, if you have a small number, then it's not good. And the higher number you have, the better your code is doing. So if you have less than 10 maintainability index, then it's bad. If you have more than 20, then it's good. And our code example had around 70, so our code is doing very good. But, it shouldn't be a surprise. And as I've said, the number of metrics is different from company to company, and everyone basically decides for themselves what they find to be most important and what they want to measure. So in the metrics, you can put the amount of sentry issues that your code produces. Additionally, you can track unit test coverage percentage. Or you can even try to calculate WTFs per minute during code review. But this metric will be a bit too hard to automate. So now you know what metrics are and what reference values you can use, but what to do with them. And the general idea here is to make sure that your code quality does not degrade over time. And there are multiple ways on how you can do that, and luckily for us, there are multiple tools that can help you with that. And the easiest place to start would be to use linters. Linters will highlight to you the potential problems in your code. And if you want just to start somewhere, you can connect your linters and tell them to show only warnings to your developers and ask your developers to fix them when they have some free time. If you're determined to make sure that your code matches the standards all the time, you can make sure that your linters fail GitLab pipelines when they encounter an error. Or if you're somewhere in between and you don't want to spend time fixing all the errors in your old code, but you want to concentrate to make sure that the new code that you write is good, you can connect linters to only changed files. And if you're a big company that already has a lot of code and you want something working out of the box, you can purchase existing solutions. And these solutions will gather the code from you, analyze it, and show them to you in a nice format. And additionally, those solutions usually have some nice perks. For example, you can use SonarQube that, in addition to analyzing your code quality and highlighting issues to you, they will also find some security issues and show them to you. But the problem with those existing solutions is that sometimes they can get quite pricey, especially if we're looking at the enterprise plan. So if you have some free resources and free time and you want to save some money, it might be a good idea to create your own tools. Or additionally, existing solutions may not meet your needs completely. As some of you may know, at Wrike we use two languages for our front-end development, TypeScript and Dart. And unfortunately, we didn't find an existing solution that supported both of those languages. So we had to go the hard way and invent the bicycle. Now let me share with you how our journey went for us. So we divided our process into two phases, and the first one was called testing the water. As a company, we've been on the market for a while, and we've managed to write a lot of code during this time. So we wanted to understand how our code was doing, whether the situation was very bad or very good, before we started to ask our developers to take some actions. And we were aware that there are existing packages to calculate metrics, because at the time our developers, my colleagues, were working on creating such a package. It was called Dart Code Metrics. So we decided to use this package to collect the metrics to help us do that. And since we knew that such packages existed, we just needed to find an alternative for TypeScript, and it was the Typhoon.js ES complex. And since those tools were from completely different developers, they produced output in different formats. So we had to unify the format of the reports as well as enhance the data, because one report had the metrics that the other one didn't calculate. So the report format looked like this. Basically had a JSON, and for every file we calculated the amount of errors and warnings for each metric, as well as additionally we calculated the lines of code. And on the repository level, we stored the same aggregated data. So for every metric, we stored the amount of warnings and errors, as well as the total lines of code in the repository. And after that, we configured the automatic collection of the metrics. So every time the code was pushed into the master, the metrics were recalculated and pushed to our database. And after that, finally, we decided to create a report to view these metrics in a nice way. So the portal to view the metrics looks like this. We have metrics, and for every metric we show the number of warnings and errors. And additionally, we invented some sort of a metric called code quality rating, which is one number that helps us to identify whether the code in this repository is good or not. So this metric was used. And, it even had some healthy competition between developers, because everyone was like, oh, my code is 5 stars, so I'm doing very great, and make them feel proud about themselves. And if we press on one of the metrics, we could see the way how the metric changed over time, if the amount of warnings first has decreased or not. So at this point, metrics were serving an informational purpose. Our developers could look at the metrics and, just understand how their code was doing. Additionally, our technical leads used the metrics to understand the code quality in the repositories that they owned and find the repositories that needed the most attention. Additionally, at Wrike, we have 20% of time in the sprint reserved for technical debt, and this time could be spent to improve code quality in the repositories. And all is great, but we're not doing an important thing. We're not making sure our code does not degrade automatically. So this brings us to phase 2, controlling the quality. And the logic here is quite simple. We fetch metrics for the master, we calculate the metrics for the current branch, and then for every metric we compare the amount of errors, and if the amount of errors has increased, then we fail the pipeline. And if you're going to follow our footsteps, it's up to you how strict you want to be. You can even concentrate only on the increasing the amount of errors, or you can pay attention to the warnings as well. Or you can even implement some threshold that will allow developers to increase the amount of errors only by 10%. So as a result, now our developers see a message like this if they run the linters locally, or when they push their code to the branch, the linters failed on CI. So basically, when we found a new problem in an existing function, we showed how the value changed and why actually we're showing the error. And if we found an error in a new record, we're showing the value, and once again we show the reference value so it will be clear for developers what we are expecting them to do. So now our developers can't push bad code into the master. Now let's summarize everything that we've talked about. So good code is maintainable code, and it should be so from the very beginning. And you should ensure maintainability using code quality metrics. And the list of code quality metrics can include the number of methods in a class, the number of arguments in a function, and so on. It's up to you what you put there. And the general idea here is that you have to make sure that the code quality does not degrade over time. And there are multiple tools on how to do that. And you can use linters, you can buy existing solutions, or you can create your own tools. And this is something that we did at Wrike. So it was, a long path, but in the end, we ended up with a tool that fit us perfectly. So I suggest that you do the same thing and create your own tools. Thank you very much for watching this video. If you have any questions, please leave them in the comment section. And don't forget to answer the question that I've asked you in the beginning. And don't forget to subscribe to this channel to get more technical content.